Welcome to this deep dive. We're taking on another complex AI topic today and aiming to, break it down for you.
That's the plan.
Today, it's all about large language models,
Yeah.
the LLMs everyone's talking about. Specifically, we're looking at scaling laws and this really fascinating concept called emergent behavior.
Exactly. We're going to dig into how these scaling laws try to predict what bigger AI models can do.
Try being the operative word.
Huh. Yeah, sometimes. Because we'll also look at where they fall short, especially when these models suddenly, almost out of nowhere, show off abilities they didn't seem to have before.
Right, and the materials you sent over, they really drive home the massive excitement, the investment pouring into LLMs right now. And it seems like these scaling laws are a big part of that fuel.
They absolutely are. They promise a kind of predictable progress.
Yeah, it's that tension that really struck me. You've got these laws saying, okay, add more data, more compute, bigger model, and voila, better performance. Seems straightforward.
Uh-huh. A nice, smooth upward curve.
But then, bam, the models start doing things, maybe things the researchers didn't even fully expect. And that's this emergence idea we need to unpack.
So that's our mission for this deep dive, right? To really get a handle on the relationship between scaling laws and emergent behavior. Like, why does it even matter if the predictions aren't always perfect, if these surprises happen?
And what's the latest thinking? What are the newest studies telling us?
Yeah, we'll look at how tweaking model size, data set size, and, the sheer amount of compute power changes what these things can actually do.
Okay, let's get into it. First things first.
Yeah.
What exactly are scaling laws? Lay it out for us.
Okay. So think of them as these empirical relationships, basically patterns people observed again and again.
Patterns linking what to what?
Linking the key ingredients, the model size, usually measured in parameters.
Billions of parameters nowadays.
Or trillions, yeah. So size, the amount of data it's trained on, the data set size, and the compute power used for training. Linking all that to the outcome.
And the outcome is usually how good it is.
Pretty much. Usually measured by loss, like how often it gets things wrong, specifically predicting the next word, or sometimes accuracy on specific tasks. Lower loss is better.
Got it. And this wasn't always known, right? There were some key moments.
Definitely. The Kaplan scaling laws back in 2020 were a big deal. They were among the first to really nail down this clean power law relationship.
Power law. Meaning?
Meaning, essentially, if you plot things on the right kind of graph log scale, you see a straight line. Double the compute or the data or the model size, and you get a predictable drop in that loss metric. It suggested a really orderly, almost engineering-like path to better AI.
Okay, that sounds like music to investors' ears. Predictable improvement.
It absolutely was. But then things got a bit more nuanced. Enter the Chinchilla scaling laws in 2022. Hoffman and colleagues.
Right, I remember that one making waves. What was the key difference?
They argued it wasn't just about making the model bigger parameter-wise. The real bang for your buck, compute-wise, came from training maybe a slightly smaller model.
Smaller.
Yes.
Interesting.
Yeah, but on way more data. More tokens. Their Chinchilla model, 70 billion parameters, which is big, but not the biggest, even then outperformed the much larger GPT-3. Why? Because it was trained on a massive 1.4 trillion tokens.
Wow. So the insight was data, 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 more tokens per parameter.
Exactly. It shifted the focus. Maybe we were compute limited before, but Chinchilla suggested we were actually data limited for the size of models we were building. Smart use of data, smart token allocation could be more efficient than just scaling parameters endlessly.
And these laws, Kaplan or Chinchilla style, they hold up across different sizes.
That's the really striking part. They seem to hold across like 7 orders of magnitude. From tiny research models to these absolute behemoths, the basic math seems to work.
Which has huge practical consequences.
Oh, absolutely. If you believe these laws are reliable, you can start forecasting. What kind of hardware do we need next year? How much will training cost? Where should we put our research bets? It gives you a framework.
Makes sense. Where's the catch? You mentioned a catch.
Yeah. The catch is emergence. Despite this beautiful, predictable curve for overall performance, sometimes these models just suddenly learn things. New skills pop up that weren't really on that smooth trajectory.
Okay, so let's get into the math a bit then. You said that helps explain the limits.
Right. So the basic scaling law equation often looks something like L equals alpha times C to the power of minus beta.
LAOZC.
Where L is the loss, C is the compute, and alpha and beta are just numbers you figure out from experiments. They tell you how steep the improvement curve is.
And on that log graph, this gives you a straight line. Nice and predictable.
Looks predictable, yes. But there are two big limitations or maybe nuances we need to understand.
Nuance one.
The power law describes average performance. Think overall GPA. It doesn't tell you how the model does on, say, calculus versus history.
Ah,
So a model might get steadily better at predicting the next word in general text, smooth improvement. But its ability to do like multi-digit multiplication might be 0, 0, 0, and then suddenly jump to almost perfect. The average hides that jump.
so the overall trend line is smooth, but specific skills can have these earthquakes.
Good analogy. Exactly. And the second nuance, highlighted by folks like Ruan and others more recently around 2024, is this idea of a sigmoid substructure.
Sigmoid substructure. Sounds technical.
It just means that if you zoom in on individual specific task microtasks, the performance curve often isn't a straight line improvement. It's an S shape, a sigmoid.
An S shape, like slow start, then fast improvement, then plateaus.
Precisely. And that steep part in the middle of the S, that's often where the magic happens. That rapid improvement phase is where you often see these emergent abilities really kick in. The overall power law smooths over all these little S curves happening underneath.
Okay, that's a fantastic image. The big picture looks smooth, like a thermometer slowly rising. But if you look at individual skills, you see these seismograph-like jumps hidden within the average.
Exactly. Take that multi-digit arithmetic example again. Accuracy might hover near 0 for ages as you scale up compute. Then, boom, between one model size and the next, it hits 98%. The scaling law might predict some general improvement, but not that sudden leap from nothing to almost perfect.
So it misses the drama.
It misses the drama.
Right.
Which brings us to defining emergence properly. How do we know it when we see it?
Yeah, what counts as emergent?
Jason Way offered a pretty useful working definition. He basically said an emergent ability is something that's like absent or non-functional in smaller models, but then reliably appears in larger ones.
So it's not just getting better at something, it's going from not doing it to doing it, like an on-off switch flipping at a certain scale.
Kind of, yeah. It's a qualitative shift, not just quantitative improvement. And we've seen some pretty clear examples over the last few years.
Like what?
Well, chain of thought reasoning is a big one. Getting the model to explain its thinking steps. Early models like GPT-2 couldn't really do it effectively, but then with larger models, it became a really powerful technique.
Right, prompting it to think step by step.
Exactly. Or tool use and code generation. You know, models around 6 billion parameters might generate snippets, but often buggy. Scale up to, say, 175 billion parameters or more, and suddenly they can write much more complex functional code or use external APIs.
Okay, yeah, that feels like a real step change.
And another one is long horizon planning, thinking through multi-step tasks. Again, early transformers struggled, but the massive models, over 1 trillion parameters, are starting to show surprisingly decent capabilities here.
So these aren't just minor tweaks, they feel like fundamentally new skills appearing. What's actually causing this? What are the drivers behind emergence?
Seems to boil down to two main things, as far as we understand it now. First is capacity thresholds.
Meaning the model just needs to be big enough.
Essentially, yeah. The neural network needs enough parameters, enough neurons, to even have the potential to represent the really complex patterns or dependencies required for these advanced skills. Below a certain size, it's like the hardware just isn't there. Like trying to run complex physics simulations on a pocket calculator.
Not enough memory, not enough processing power. Makes sense. What's the second factor?
Data diversity. So even if you have the capacity enough parameters, the model needs the right kind of learning experiences. It needs to see enough varied examples in the training data.
Ah, so it needs the raw potential and the right training.
Exactly. And this connects back to Chinchilla. They showed that if you flood a model with more diverse data, more tokens, even if it's not massively bigger in parameters, you can sometimes trigger these emergent abilities sooner. The data helps sculpt the connections within that available capacity.
So you need the gunpowder, the parameters, but you also need enough of the right kind of spark the diverse data to ignite it.
That's a great way to put it. Fuse, gunpowder, ignition parameters, and tokens working together.
Okay. But I remember reading something about maybe sometimes these jumps aren't quite as dramatic as they seem. Something about how we measure them.
Ah, yes, the metric illusions idea. This came up in work from Stanford HAI, among others. It's a really important point.
Metric illusions, meaning the way we measure tricks us.
Sometimes, yeah. It depends on the metric you choose. Think about that arithmetic example again. If your metric is just exact match accuracy, did it get the answer 100% right, yes or no?
Okay, a binary measure.
Right. A model might be getting progressively closer to the right answer. Maybe it gets the first few digits right, then more, then almost all of them. But your binary metric won't show any improvement until it nails every single digit perfectly.
So it looks like zero progress, zero, zero,
Mm-hmm.
then suddenly 100%, even though it was learning gradually underneath.
Exactly. The harsh metric creates the illusion of a sudden jump. It's like only checking if a light switch is fully on or fully off, you miss the dimmer switch being turned up gradually.
So what's a better metric in that case?
You might use something more nuanced, like log likelihood, which measures how confident the model is in its prediction, or maybe measure the number of correct digits. These smoother metrics might reveal a more gradual improvement curve that the yes-no metric completely hid.
Okay, that's crucial context. But are you saying all emergence is just a metric illusion?
Oh, definitely not. No. While some cases might be explained or softened by looking at metrics, others are undeniably real. When GPT-4 started writing functional React apps from a simple description, that wasn't just getting one more digit right in a calculation.
Yeah, that feels qualitatively different.
It really does. So metric choice matters, we need to be careful, but it doesn't explain away everything. There are genuine leaps happening. Which brings us to the latest developments, because this field moves so fast. What's new in, say, 2024, 2025?
Yeah, how is our understanding of these laws evolving right now?
Well, things are definitely getting refined. Remember the Chinchilla finding about the optimal ratio of data to model size?
More tokens per parameter was better?
Right. Well, recent work, like from the mini CPM team, pushed that even further. They found that using an even higher token per parameter ratio, much higher than Chinchilla suggested, allowed their smaller models to learn incredibly fast, sometimes outpacing larger models trained on less data per parameter.
Interesting. So maybe the optimal ratio wasn't optimal after all, or depends on the model?
It seems so, or at least we're still figuring it out. And then you look at models like LLaMA 3 and presumably LLaMA 4, and they seem to be using enormous token counts relative to their parameter size, way beyond even Chinchilla's ratio.
Which suggests.
It suggests that maybe even our big mainstream models have been, in a sense, undertrained or undersampled on data relative to their capacity. We might get more out of them with even more data.
Fascinating. What else is new?
Mixture of experts MOE architectures are becoming much more prominent.
Right, the idea of having specialized subnetworks.
Exactly, like a committee of experts. Instead of the whole giant model processing everything, you only activate the relevant experts for a given task.
More efficient.
Much more efficient compute-wise. And they have their own scaling laws. Performance seems to scale not just with total parameters, but with the number of active experts. It lets you build models with huge total capacity without the training and inference costs scaling quite so brutally.
So a different way to get scale focused on specialization.
You got it. And we're also seeing scaling laws being explored and validated beyond just text. Vision language models, like the recent Gemini and Claude versions, show similar scaling principles apply when you combine images and text. The exponents might be different, the specifics vary, but the core idea holds.
Scale still matters across modalities.
It seems so. And the common thread in all this recent work, when researchers apply these updated understandings, better data ratios, new architectures like MOE, they often find that emergent abilities pop up sooner or more efficiently than the older scaling laws would have predicted.
So refining the laws helps us find the emergence faster.
It seems that way. Better scaling leads to earlier, more efficient emergence, which leads us to a pretty deep, almost philosophical question.
Uh-oh. Philosophy time.
Just a bit. As these models get so capable, following these scaling laws, showing emergence, are they actually understanding things? Or are they just becoming unbelievably sophisticated mimics?
The imitation versus understanding debate. Yeah, that's a classic.
It is. You know, when a smaller model spits out nonsense, we dismiss it. But when a huge model writes a plausible legal brief or debugs complex code, it really makes you wonder, is there understanding there? Or is it just brilliant pattern matching based on trillions of examples? You might think of Searle's Chinese room argument here, maybe.
The idea that manipulating symbols doesn't equal understanding.
Right. But, you know, there's also a more pragmatic viewpoint, maybe closer to someone like Jeffrey Hinton's perspective,
Which is?
which is maybe focusing too much on whether it's true understanding, like ours is missing the point. Maybe intelligence is more like a bundle of capabilities of affordances. And as you scale these models, that bundle just gets bigger and bigger.
So focus on what it can do rather than what it is.
Perhaps. If it walks like a duck and quacks like a duck, maybe for practical purposes like safety and alignment, that's what matters most right now. The capabilities are real, whatever the internal feeling might be.
That definitely brings us to the practical side, safety, alignment. How does all this, the predictable scaling, the unpredictable emergence, impact making sure AI is beneficial and safe?
It makes it, well, challenging. It's hard to align something perfectly with human values when its capabilities are constantly shifting, sometimes dramatically and unexpectedly.
Right. How do you set safety rules for something that might suddenly learn a dangerous new skill tomorrow?
Exactly. That's why you see organizations like Anthropic developing things like responsible scaling policies. The idea is that as you train bigger and more capable models moving along that scaling curve, the safety checks, the evaluations, the red teaming have to get progressively tougher.
So the hurdles get higher as the potential power increases.
Precisely. There's an emerging consensus, I think, in the safety community. Things like much more rigorous pre-deployment testing for larger models, maybe requiring external audits like SOC2 or ISO certifications once models cross certain capability thresholds linked to scale.
What about specific capabilities like that tool use you mentioned?
Yeah, especially for potentially risky capabilities like interacting with the real world or executing code, there's a lot of focus on needing things like robust kill switches, strict permissions, and constant monitoring. The idea is that policymakers might even start tying regulations not just to model size, but to empirically demonstrated capabilities that often emerge at certain points on these scaling curves.
Using the scaling laws almost as regulatory checkpoints.
Yeah, interesting. Okay, so looking forward, crystal ball time. If these trends continue, what kind of things might we see? And what keeps you up at night?
Well, if you just extrapolate the current curves, assuming the exponents hold, which is a big if.
Always an if. Always an if. But you could imagine AI becoming capable enough to act as autonomous lab scientists designing and running experiments, or multi-agent systems tackling really complex research problems collaboratively. Maybe even code bases that can largely debug and improve themselves.
That sounds transformative.
Yeah.
For good and potentially otherwise.
Exactly. Which leads to the big unknown, the thing that causes concern.
Which is?
Will our ability to ensure these incredibly powerful systems remain aligned with human interests keep pace with the rate at which their capabilities are growing? That's the billion-dollar question, maybe trillion-dollar.
Can wisdom keep up with power?
Essentially, yes. The same scaling laws that predict these amazing capabilities also predict the potential for increasingly powerful and potentially unpredictable emergent behaviors. Hinton has famously warned about this, about the potential for humanity to become transient if we can't manage this transition.
A sobering thought.
It really is. It just underscores this dual nature we've been talking about. Scaling laws are incredibly useful, powerful, predictive tools, but they also conceal these moments of sudden, perhaps revolutionary change in what AI can do.
Okay, so let's try to pull this all together. Our deep dive today really explored scaling laws in LLMs, how they give us a kind of roadmap connecting size, data, and compute to performance.
Right, a valuable framework, but not the whole picture.
Because they don't fully capture emergent behavior, these surprising leaps in ability that just seem to switch on as models get bigger.
Leaps driven by things like hitting necessary capacity thresholds and, crucially, being fed enough diverse data. And our understanding of the right way to scale the best recipes is constantly evolving.
Yeah, the Chinchilla insights, the newer findings on token ratios, MOE architectures, they all refine the laws and seem to bring that emergence forward.
Leading to that tension. The predictable march of scaling versus the unpredictable sparks of emergence. It really defines where we are with AI right now.
Absolutely. We've got these amazing predictive tools, but we also have to stay humble and ready for surprises.
Couldn't have said it better myself.
So here's a final thought to leave you with, building on that potential for surprise. As AI continues to scale, potentially exceeding our predictions and showing abilities we didn't foresee, what core beliefs about intelligence itself, maybe even our own place in the grand scheme of things, might we eventually need to rethink?
Deep question to ponder.
Definitely something to think about. If you want to dig deeper into the research papers and articles we touched on, do check out the further reading list for this deep dive. Thanks for joining us.